Good afternoon, everyone. Welcome to this week's ITC Luncheon. Avis traveling today will be your host. We just heard a fantastic colloquium by Brenda Frye from the University of Arizona, who told us about supernova hope, type 1A supernova that was used to measure the Hubble constant. And we have a great lineup for today, but before we start, we have a little announcement about a Scary Graphics pizza lunch for Halloween. So, Alisa.
Hi. So if you are a graduate student or postdoc, you will have hopefully gotten an email that looks like this. And so what we're doing is on Halloween, we will provide pizza for lunch for anybody who has an interest in improving their visualizations or improving someone else's visualizations. And so there's a way to upload that in advance, and we have a limited number of spots, and some are gone, but some are not. And so I just brought a few of these handouts, and so I'll just leave them on the corner here. And anybody who's interested, sign up quick so you get a spot at this. Thanks.
Yeah, thank you. I was saying we have a great lineup for today. We will start as usual with our colloquium speaker, Brenda Frye, who will be with us today and tomorrow. So if you want to meet and talk with Alisa, please sign up on the Google Sheet. Then we will continue with Eva Paulsen, graduate student from the University of Chicago, who will tell us about the variance cycle in low mass galaxies. Then the third speaker will be Helena Richie from the University of Pittsburgh, talking about simulating the dusty universe, frontiers in our understanding of the source and nature of extragalactic dust. And finally, we will conclude with Jacob Nibauer from Princeton, telling about constraining dark matter with stellar stream kinematics. So let's start with Brenda. Please take it away.
Yeah, hello, and thank you. I thought to arrange a discussion that we could have that could include people from different fields. So hopefully this will be one that is engaging, and do feel free to interrupt. But it does make use of gravitational lensing, which is something I can't seem to escape with any of my projects. So let's get started. So as we all know, if you can consider maybe a strong lensing scenario in which there is a galaxy in the background whose light is intercepted by a foreground massive lens, then there can be a magnification of size and brightness of that background galaxy that is typically circa 10 or factors of tens, something like that. If it's 100, then you should request the uncertainties on that value. So here's one example of a galaxy, which is called the Sunrise Galaxy, that has, at the time, it had a photometric redshift of 6. And you can see that that one galaxy, which would have a size approximately equal to the thickness, in the case of pure tangential stretch, ends up being stretched into a giant arc that you can see with an angular extent of 16, 17 arc seconds in this case, a really dramatic one. And if, say, star-forming knots can be identified, which are these ones here, such as 1b, 1a, then if those knots are also situated rather near the Einstein ring, or what we call the tangential critical curve, then they can be further magnified up to factors of 100 to 1,000. And in some cases, there are even individual stars that are magnified by 1,000 to 10 to the 4 that have been detected at cosmological distances. One of the more famous ones might be Icarus, if you've heard of that one, at redshift 1.5. But today, I'd like to talk about one particular claim, which was the most distant single star in the universe. It's called Earendel, right here. And it has this photometric redshift of 6. And I think what brought a lot of attention to it is that when modelers constructed a lens model for this cluster and this giant arc, and they asked, what would the source plane size constraint be for this Earendel object? It's returned less than 0.02 parsecs. Not a lot of room for a star-forming cluster, for example, but enough room for a single star, binary star, something like that. So this claim held out, and then the idea arose, okay, if it's a single star or a binary star, then the expectation is that you should see flicker. You should see variability over time as that single star gets lensed not only by the massive galaxy cluster intervening between us and the source, but also by micro-lensing sources near the caustic. Okay. And that variability then, wasn't detected. So there's this puzzle, what could Earendel be, given that there's not variability detected, at least over 2-year timescales? Should we wait longer? Should the object be something else? What is going on here? Okay, so I might need your expertise as stellar astronomers and everyone else. So an exploration was made that says, okay, well, current lens models, like the ones I described during the colloquium, are called macro lens models. We take typically we take the objects that we can see, which are galaxies, and we say that dark matter underlies them. And we make the assumption that the dark matter follows the light. And once we don't see any more sources of light, then we stop adding mass points. But according to lambda CDM model, obviously there should be dark matter subhalos that are even smaller than 10 to the 10 solar masses, which is typically where we start. And we should expect a distribution of them going all the way down the scale and certainly down, further and further down. And then it was brought up over the past few years that if if there is this population, then that population can dominate the lensing strength, okay, and still meet our constraints on the deflections. So what happens if we introduce these smaller deflectors? Well, what happens is it essentially kind of weakens this the macro caustic, the Einstein ring, and in doing that, we're able to get a different size constraint on the source plane that extends up to 3 parsecs. So if we had this different size constraint, then perhaps we could allow for a different object type to be considered for the Earendel discovery. So this is my final slide here. So my graduate student, Massimo Pascali, was looking through the archives and discovered spectroscopy in this field that hadn't been analyzed or published. So we reached out to the PI, and they said, go ahead. So we got the data. The first thing we did is he found that there's this young stellar cluster called SFCB, according to some other authors. We didn't make this naming. Star-forming complex. Okay, and that star-forming complex is a very young star cluster with multiple emission lines: H beta, O3 doublet, O2 doublet, neon 3. So we were able to measure this first spectroscopic redshift of this giant arc, which is 5.926. So it was consistent with the photometric redshift of 6.2, plus or minus some change. And the second thing we did is we were able then to download the spectrum. I'll show you again if I don't mean to be flipping too much here. We're able to download the spectrum for Earendel and the spectrum for 1A adjacent to it and 1B. 1A and 1B are named that way because they are multiply imaged star-forming knots along this giant arc. It has a critical curve that weaves in and out of the giant arc. Okay, so the data for 1B is a little bit brighter, a little bit higher signal to noise. So I'll show you the data for 1B and for Earendel in the next slide. Okay, so we found we could take this spectrum and we could fit simple stellar populations to this spectrum using 3 really well-known spectral libraries: FSPS, which is run right here out of this department by Charlie Conroy, and BPAS, it's called, and Bruzel-Charlot O3 stellar libraries. And all 3 of them returned an interesting result, some differences in the details, but the interesting result that both of these systems are extremely well fit to a star cluster rather than an individual star. And the star cluster would basically, with some differences, be of intermediate age, so not showing the multiple emission lines like the star-forming complex further along the long axis of the arc, but instead it had some intermediate age estimates of tens of megayears, rather low metallicity, about a tenth solar, and interestingly, our estimate for the formation age of these objects as a function of metallicity actually lies on the age metallicity relation for globular clusters within the Milky Way. So we are exploring now whether this set may be added to a growing set of other claims of star clusters at high redshift that may be progenitors of globular clusters in the present day. Okay. And that is my introduction to Earendel. Curious to hear what you think.
Thank you, Brenda, for another great talk. We have ample time for questions.
Yeah.
Let's start from here.
So the sunrise arc, you would say, is a disk. It's a disk galaxy, and these complexes are on the...
Well, the sunrise arc, the sunrise galaxy, yeah. It's not yet what I would say on the Hubble diagram at redshift 6. It's a galaxy, yes.
This galaxy, and these things are on the...
Well, it's star forming for sure. Star forming for sure. Yeah, I don't know of a good source plane image that's been made for it, but let's see what you think. Yeah. Sorry. Yeah.
Hi, great talk. So the suggestion, or there, there's this implication that 1A, 1B, and Earendel are probably the same source.
Well, they're the same source. Yeah.
Oh,
yeah.
Yes.
Yeah.
So how does that modify? Does that modify the lens model then?
Well, it is a constraint for the lens model. It's how we're able to construct the lens model is by using exactly those image constraints in order to do it. Yeah, and we did get it does look like when we look at the spectrum too that they're the same 1A and 1B and 1B. So I mean, one would normally stack them. I would probably stack them, but we decided just to use 1B in this case. But yeah, 1B is not only known to be mostly imaged, but it's already I would say confidently a star cluster. But ultra dense, these star clusters are coming out with densities up to 10 to the 6 solar masses per square parsec. One more question, yeah.
You said that you had to introduce these small dark matter halos. Do you also constrain the size of those halos that would you need to construct this lens model? Is that something you assume or you constrain?
Yeah, that's right. Yeah, the lens models could not. The constraint is that they could not be greatly affecting the deflection angle, so that we could maintain that same meet those lensing constraints. Yeah. Ramesh, yeah. Oh, sorry.
Sorry, was there somebody else?
No.
Okay.
Yeah.
You said 1B was brighter than 1A.
A little bit, yeah.
Yeah, little bit. How little is that?
Well, that's a good question. I don't know for sure because I also don't remember if there were slit losses for one versus the other, right? You can see where their position is on the MSA micro shutter.
I mean, the reason I was asking is these are two nearby images with the other guy very far away.
Right, almost converging.
So they're almost across the critical curve.
Right.
That's when you expect them to be equal.
Sure, yeah.
So I was just wondering, is this pushing the models in any way, the brightness ratio?
Yeah, well, the bright, not quite so much because they're, you expect them certainly be equal, certainly as one really approaches the critical curve. And by that we mean within typically a couple tenths of an arc second or something. And you can see that these are even bigger ranges. Let's take a look. You can see this, the angular extent between 1 and B is perhaps even a bit longer than 2 arc seconds.
Yeah, but I don't know arc second is a good scale because that comes from galaxy.
Sure, no, I understand.
Lensing.
But
Here the whole scale is different. So I would call these actually pretty close.
Okay, well that's good. Yeah. Well, they don't look significantly different to me, but I'll have to get back to you because I don't recall what the magnification ratio was relative to the spectroscopy. Right. I want to make sure we take into account the slit losses, and I don't remember what the answer was for that right now.
We have time for one final question while Eva sets up the next slides. Yeah.
Thanks for the great talk. I was just wondering, from the stellar modeling side of things, given the metallicity we're looking at, shouldn't this star have a lot of mass loss and there should be really broad emitting lines? So would that be one way of ruling out the star here? Because even if it's 30, 40 solar masses on the very conservative scale, there should be strong lines of mass loss. think that should be
Well,
quite
we-
evident.
So I don't know what you mean by ruling out. So first of all, we do see strong emission lines from this
Can
galaxy.
you repeat the question?
Okay. Can you repeat the
Oh,
question?
yeah,
Some
sorry.
people can hear.
So,
Yes.
just need to say is that since the metallicity is like 10th of solar and it's a really massive star, there should be strong line-driven mass loss in the star. And the width of the line, I don't know exactly what it will be, it should be a lot. So you're saying that you can like see road emission line,
Well,
but
the
still.
star-forming complex shows several emission lines,
Mhm.
which would not be resolved in the unlensed case, right? This offers the only opportunity really to jump into the interstellar medium and trace what happens along it. So we do see many emission lines. I don't know how broad you define it broad. We see a lot of them. And we don't see evidence, we would not be able to see evidence, say, of wind features, which is what you might be describing, because the resolution of near-spec prism is not high enough to be sensitive, say, to the, say, to carbon-4, PCM profiles or something like that. Is that?
Yeah.
Yeah, okay.
All right, thank you, Brenda. And now we have Eva Paulson from the University of Chicago. Take it away.
So I'm a final year graduate student.
Did you switch on the mic?
Oh, is it not on?
It's on
Did
top.
I turn it on? I probably turned it off. Oh, it's not on. Thank you. Thank you, Scott. Yeah, so hi everyone, I'm Eva Paulzine. I'm a final year PhD candidate at the University of Chicago, so I'm really happy to be here today talking about some of my work. Now, I do both observations and simulations, and today, A, it is the ITC, and B, this is work that I've done with your very own Vadim Semenov, and so it felt right to talk about this today. So really, when I say the baryon cycle in low mass galaxies, which was perhaps a little bit optimistic as a title, this is really the small scale baryon cycle in low mass galaxies. Now, I want to, kind of justify this to everybody here, but when I talk about low mass galaxies, I'm going to make a lot of statements about low metallicity gas, and that's for a couple of reasons. So here is the mass metallicity relation. Most people have probably seen some kind of version of this. This one happens to go to high redshift. There's a reason for this. So on the left side of this plot, you get to lower masses, and particularly where you're looking at these kind of neon blue, neon pink curves. This is telling you what the mass metallicity relation is for local dwarf galaxies at like redshift 0. If you go to the right side of this plot, you go to higher masses, but you're looking now at things that are at redshift 6, 7, 8, even maybe a little bit higher on here. 9 if you believe it. This is a paper from 2023, so those are all probably photoz's still. But what this is really saying is when we're thinking about low masses locally and just galaxies in general at higher redshift, we are thinking about this low metallicity universe. And this is, of course, because we have small potential wells that are very susceptible to having metals blown out. They don't retain metals very well. At the same time, global gas metallicities were low in the early universe. But I want to justify that basically everything that I'm going to talk about for low mass galaxies, we think for self-similar gas in low metallicity galaxies broadly, including at high redshift, will be relevant. Now, I know that low metallicity distinction can be a little bit iffy depending upon who you talk to, because certainly the POP3 people will tell you what I do is not low metallicity. But I'll just draw the line here at 10% of solar, just because it's a good place to draw the line, and also there's an interesting feature there that I'll point to in a moment. So in all galaxies, we think star formation happens something like this, where we have this interplay between local feedback processes, local gas densities, and perturbations in that gas density, certainly cooling, and then you have these kind of ejective properties where you have both winds from massive stars, but also from supernovae. You have all sorts of mechanical feedback and photoionizing feedback in those cases. And then if I were to talk about the full baryon cycle, I would also tell you why it's interesting to think about the jets that are launched or the winds that have actually created these galactic scale environments in these low mass galaxies. I won't talk about that today. But I will talk about pretty much everything in blue, or maybe not quite everything, but most of the things in blue. But the thing to note is that really in this HabEx report figure and in our kind of classical picture of star formation, we're thinking about star formation primarily happening in molecular clouds. And that makes sense. At high redshift, oh my gosh. At high masses, we do see that. We see the molecular Kennecotte-Schmidt relation. We know that that's cold gas. We know that's a very low energy state of gas that makes it very easy for it to coalesce into stars. But there's a problem with it when we start thinking about low mass or low metallicity galaxies. Molecular hydrogen is much less abundant when you start looking at low metallicity gas. Now, this is a very simple sort of first order approximation from our Krumholtz here, but what happens is because the cooling is so different where you don't have metals, you end up taking much longer to reach the sort of equilibrium timescale of formation of H2. And so for a typical giant molecular cloud at low metallicity, the lifetime of that cloud is then much shorter than the average formation time of molecular hydrogen. And this poses a problem. You just don't have time for that molecular hydrogen to build up in these clouds before they dissipate. So that means that as you go to lower metallicity, again, roughly to first order, this should be an inverse relation where you have, at low metallicities, much longer formation times, and so lower H2. But we still see what I would call normal star formation in low metallicity galaxies. Now I say normal, and I realize there's no such thing as normal star formation. I think everyone will agree with me on that. All galaxies form stars or don't form stars in their very own ways. But when I say normal star formation, I mean that we see active star formation in very molecular gas poor galaxies. So there are a couple of examples here, UGC 9282, which I think has CO measurements of it. One's Wiki 18, which is emblematic of this class of blue compact dwarf galaxies that are very, very low metallicity and yet extremely starbursty. And then, of course, Leo P. This was a recent Nature paper from Grace Telford where there are direct measurements of rotational H2 with MIRI. And so we're starting to really be able to look in depth at these low metallicity environments and say, okay, do we actually see star formation? Do we see H2? And the answer is, for instance, with Leo P, where we have a direct measurement of the H2, very low H2, but it's forming stars at approximately a normal rate. And so this does kind of pose a picture if you're thinking about star formation as tied specifically to molecular hydrogen. Now, one way that you could test this, because there is kind of a paucity of observations, would be to use Vadim's excellent simulation, where he's actually been able to recover the very frankly detailed properties of star formation, not just the Kennecotte-Schmidt relation, but also this decorrelation of gas and young stars on small scales. So the feedback is correct, and as correct as it can be. It's realistic in this high-resolution simulation. And the star formation is not based on molecular hydrogen. It's instead based on this virial parameter. So basically, how likely is that gas to collapse as a function of density, as a function of temperature? Now, I reran this at a number of different metallicities, basically ranging from 0.01 times solar all the way through solar metallicity. The fiducial run is on the right side here, which is Vadim's NGC 300-like run. And we see structural changes in the ISM certainly as we go to different metallicities. But the other thing that we see that we expect to see is that there is this metallicity fall off. So the metallicity falls off very quickly, below about 10% solar. I'd be remiss not to mention that we do have a model for this if you wanted to do this in your own simulations or even with observations. But we see this. We see that, again, kind of linearly with metallicity, we have a lowering of the molecular hydrogen fraction. At the same time, this H1, H2 transition starts to occur at higher densities as you go to lower metallicities. It's harder to form H2. But what we don't see at the same time is the star formation rate fall off. So the star formation rate does fall off, but it falls off by about a factor of 10 over a factor of 100 in metallicity, where the depletion time of H2 falls off by about a factor of 100. So the H2 fraction is changing, but the star formation rate is not. And if we look at that in the context of this kind of phase space, so you can see temperature is the color bar here, gas motion, which you could use as a proxy for the strength of turbulence, et cetera, is on the y-axis, and then density is on the x-axis here. And if you go to the lowest metallicity case versus higher metallicity cases, if we use this line as kind of a guide, it's not a stringent cut, it's just a guide for where star-forming gas is occurring to the right and below on this line, then you have much less gas that is capable of forming stars, but it's because it's not as cool and not as dense, not because it's not molecular necessarily. And so we actually find that in kind of cold, dense gas, regardless of its properties, regardless of if it's H2 or atomic hydrogen, as long as it's cold and dense, the star formation efficiency, or like the fraction here, it's epsilon FF, so it's the fraction basically of stars forming out of that gas, the fraction of that gas forming into stars. It's approximately 1%, regardless of galaxy properties. Doesn't matter the density, doesn't matter the metallicity, even the UV field strength, it doesn't care. And so this is emergent in the simulation. This is not something we tune for, but you can see metallicity, there's no dependence, that's on the left there. Density, there's very little dependence. The UV field strength is a correlation, not causation. I'm happy to answer questions about it, but I don't want to run out of time. It's approximately 1%. And this is due to self-regulation. So this self-regulation we test in a sort of dumb way, which is to say that we turn off turbulence. This is one way of basically taking that kind of energetic feedback that we have, not accounting for it in terms of its compressive force. And this way we're only accounting for cooling and for the kind of native gas densities in deciding what will form stars. And you see that there's now a metallicity dependence. That metallicity dependence happens to correspond to where molecular hydrogen falls off because there is this cooling consideration. And you also get an enhanced density dependence because now this is the thing that's really, it's density and it's temperature that are driving your gas behavior. So if the non-turbulent kind of physical runs are flat, there and grayed out, but you can really see how strong this is as an effect. And if we look at the PDFs showing basically what this is the last slide, what the star formation efficiency looks like in the physical run on the left and in this kind of non-physical, non-turbulent run on the right, we can see that there's now a metallicity dependence, which to us means that A, star formation is not dependent upon the molecular hydrogen, but it is dependent on cold dense gas. And B, the star formation efficiency is universal because of the interplay between turbulence and feedback. Thank you.
Thank you, Eva. Let's start from Alisa.
So it's very interesting. In local star formation maps these days, it's becoming clearer and clearer that the idea of big fluffy molecular clouds with little clumps that sit there and form stars is totally wrong.
Yeah.
And so I'm just curious whether the idea that there could be these little accretion knots that would be forming stars that might have a lot of H2, is that ruled out? Like the resolution of the simulation is good enough to rule that out?
Yeah, so this is a 10 parsec resolution, so we would never be able to rule that out. I think my feeling on this is because we know the bulk abundance. We don't know, for instance, that H2 isn't preferentially forming stars, but we do have contexts where we have gas cells that have so little H2, but we're still forming stars out of them, that you would have to expect that at least some of that star-forming material is coming from a neutral atomic medium. But of course, because of the resolution, you're not going to be able to rule it out.
It'd be interesting to see what happens.
It would be so interesting. Yeah. I totally agree.
Eric, yes.
I was just wondering, the turbulence, isn't it self-generating because of the feedback and so on and so forth?
Turn it all off. Yeah.
How do you turn it off?
Yeah, great. That's a great question. Thank you. I basically stopped tracking any kind of contribution of feedback into turbulence or into the motion of the gas, and simultaneously, or into like the subgrid turbulence motion of the gas. So we still have radiative feedback, for instance. And I turn off the subgrid turbulence model for those runs. So they're completely non-physical. I want to be very clear. These are non-physical runs. This is just to see if the effect basically will change, or the effect of turbulence is to kind of compress gas that would otherwise not be compressed, allowing it to cool and form stars.
Kinetic energy of the feedback is generated on the subgrid level, and then you turn that
Some of
off.
it.
So
Yeah.
it doesn't propagate it to the rest of the grid.
Some of it, yeah. So we turn off the subgrid contribution from the feedback in that way, yeah. Yeah, but I do want to stress, we know it's non-physical. It's a toy model, but it seems to point to this, what other people have also found of a turbulence and feedback regulated
I wasn't
ISM.
requiring realism, I understand.
I appreciate it.
We have time for one final question. Yes.
I'm wondering about some observational consequences. Do you think there might be such a situation that you form stars in there's denser regions where some of the conditions get satisfied,
Mm-hmm.
and what happens is that you measure metallicity with the telescope in those regions because you don't see the metal poor medium around it.
Sure.
And so basically the metallicity measurements will be all elevated artificially, and if you take the mass, like the volume average metallicity will be really, really low.
Yeah, so observationally, what we've kind of pinned this on is if you look at FANGs or you look at some of these other really detailed studies of the ISM and how it, sort of the virial parameters, sort of the star formation efficiency, depending on what paper you're looking at, people have done this across galaxies, and they've done it, I wouldn't say in a way that's agnostic to that kind of metallicity measurement, but just because you are looking at galaxies with so many disparate properties, you are kind of marginalizing over it. And so observationally, we see something consistent with this. I didn't really touch on that, but there are empirical constraints also suggesting that basically on a cloud scale, 1% of that gas will form into stars over, say, a free fall time. But yeah, I mean, metallicities are hard. This is one of the things I didn't preview because it's complicated, but we're looking observationally, not at this particular thing, but measuring metallicity is controversial. Something that I don't like doing and don't like talking about. I'm kidding. But it is true. It's very complicated to do that in the gas phase. Yeah.
All right. Thank you, Eva.
Okay. Good. Okay. Hi, everyone. Thanks for having me here today. I'm super excited to be here. I'm Helena Richie. I'm a finishing year grad student from the University of Pittsburgh, and today I'm going to tell you about some of the work I've been doing to try to constrain the nature of dust evolution throughout the baryon cycle. Dust. Typically, I think when a lot of people think about dust, they think about the interstellar medium. But this talk is going to be fully focused on the circumgalactic medium because observations are surprisingly show us that there are vast populations of dust in the circumgalactic medium, which is a bit surprising because the formation mechanisms of dust are all confined to the disks of galaxies. So this figure is showing some of these observations. The y-axis is showing the surface density as a function of radial distance in galaxy halos. The blue points are showing measurements for dust averaged over millions of galaxies. And I want to draw your attention to the scale of this plot, right? It's ranging from roughly galactic scales, like tens of kiloparsecs, all the way out to megaparsecs. And so these are really large scales, and whenever you total up the amount of dust inferred from these observations and compare it with like the cosmic dust density of galaxies themselves, you'd find that they're roughly equivalent. So huge reservoirs of dust are somehow in the CGM, and this is pretty surprising, right? Because it's formed in the ISM. There must be some mechanism for transporting it to the CGM that is operating very efficiently that we don't fully understand. So I've spent my thesis investigating multi-phase galactic outflows to try to see how dust evolves throughout this process and if this is a viable explanation for our observations. And starting off with a bit of background on multi-phase outflows, I'm just going to show this movie of how this works. This is showing a slice of temperature in a simulation I'm going to talk a bit more about in a minute. But basically how these outflows work is you have these energetic supernova explosions that can go off in the disks of galaxies and drive these hot winds out at thousands of kilometers per second with temperatures of 10 to the 7 Kelvin out into galaxy halos. And in that process, they can sweep cool ISM material out from the disks of galaxies and accelerate them to these regions. So, right, because we know that these outflows are fairly ubiquitous in the universe, it seems like they might be a likely explanation for getting dust out to the CGM. But it's not straightforward to assume that this would work because these dust grains aren't exactly static objects as they move throughout the baryon cycle. they can evolve quite a bit depending on their environment, and in particular, one mechanism that people worry about affecting dust and outflows is this process called sputtering, which is basically where you have, your dust grain and a hot plasma, and these, the plasma is hitting into the dust grain, and it can gradually destroy dust by knocking off the bound atom molecules from the dust grains. So, outflows we just saw are by volume filled with this hot gas. So it's, worrisome that might destroy dust in this process. We have models for how sputtering operates on dust grains, dependent on the gas properties. So, hotter, denser gas is going to destroy dust more quickly, and smaller grains are going to get destroyed more quickly just because there's less to destroy. And you can use this time scale to come up with estimates depending on which gas phase you're in, like the hot supernova wind or this cool ISM material, to determine how quickly dust could be destroyed. So for a grain at the peak of the size distribution in the ISM, there's a huge disparity in time scales between phases. So the evolution of dust and outflows is going to depend a lot on where it exists. So I have been using simulations of multi-phase outflows to try to see how dust evolution depends on the dynamics of outflows. And I've incorporated this model for dust advection and sputtering into this hydrodynamics code called CHOIA. It stands for Computational Hydrodynamics on Parallel Architectures. And this is a GPU-based hydro code that can really efficiently simulate these large physical volumes at a fixed high resolution owing to its GPU-based construction. And so this is just driving, this figure is highlighting why we need these efficient computational codes to simulate galactic outflows. So these outflows, like we saw in the previous figure, are made up of a bunch of these clouds that are evolving based on this parsec scale hydrodynamic mixing that transfers momentum into the clouds and accelerates them out of the ISM. This parsec scale mixing is what's driving the broader kiloparsec evolution of outflows. So to simultaneously capture these scales, you need high resolution. This simulation was run in a box of 10 by 10 by 20 kiloparsecs cubed with a fixed resolution of 5 parsecs throughout the grid. So it's a lot of computational power to be able to capture all of those cells. But if you have a supercomputer, which is what this was run on, and 8,000 GPUs or something like that, you can run these simulations in about 5 hours or so. So yeah, it's just 8,000 GPUs. That's all you need. So this code, this existing infrastructure, has been an excellent tool for seeing how dust evolution depends on these gas dynamics, because we're able to simulate them to a really detailed degree. So this is the first problem that I applied this dust model to. This is looking at how dust evolves in these individual cool clouds, again, to see if this shielding in cool gas is an efficient mechanism for protecting dust as it traverses outflows. So the setup of this problem, I'm going to play this movie. You have a stationary, cool, dusty cloud that gets accelerated by a hot, dust-free galactic wind. And basically, in this simulation, you can watch that the entire time this wind is blowing in from the left side of the box and disrupting the cloud, driving these hydrodynamic instabilities and accelerating the cloud. Oh, I'm getting stuck. The dust is staying perfectly coupled to the gas throughout this process, or I should say the cool cloud is not losing any of its gas to the hot wind. Basically, the cloud is all staying clouded. In that process, it's really efficiently protecting dust from destruction, again, by the sputtering timescale, which is what I'm modeling in these simulations. And you can see on this side of the plot, I'm tracking the total amount of dust destruction that occurs throughout this simulation, and it stays exactly at 0 because all of the dust is staying in the cool gas. So that's great, but we know that sometimes whenever this ISM material is launched into outflows, these clouds don't stay clouds. They can get, destroyed by these hydrodynamic instabilities. So looking at the case of when a cloud is destroyed, I'm going to play this movie. And if it is going to play, Oh. Hello. I don't know why it's not playing. That's really weird. Never had this happen before. Okay. I'll just zoom in and then, yeah. Okay, I mean, basically what you're seeing in this simulation is just that this cloud, instead of surviving long-term and shielding all of the dust, all of this, this dust that is not co-spatial with cool material in the top panel, all of that dust is getting transferred into the wind and quickly evicted out of the box. So looking at our tracker of the sputtered mass on the left side of this plot, it's only reaching about 25%. And even though this wind is a very hot temperature that can destroy dust on short timescales, like I've mentioned, the dust is just getting evicted really quickly from the region of the wind that is most destructive to dust. So purely by a dynamical argument, dust is safe in these simulations. These cloud wind simulations were really useful for showing us what happens on a cloud scale, how the dust evolution depends on the dynamics of outflows. But what we really want to do is look at entire galaxies and their outflows, and also look at how this problem depends on the size of dust that you're launching in outflows. So this is another set of simulations that I ran. This is showing for a single galaxy all of the dust density projections ranging from larger to smaller grain sizes, moving from left to right. And I'll play this simulation, and you'll see the supernova starting to go off into the disk and driving this outflow. And looking from left to right, you could see a pretty big difference in the distribution of the dust in the simulation. So again, for these larger grain sizes, which is what we were looking at in the cloud wind simulations, the outflows are kind of homogeneously filled in the cool gas and hot gas alike of this dust, whereas in the smaller grain sizes, that dust is getting rapidly destroyed. Okay, I'll wrap it up. This is one of the main results of this simulation is that it seems from these outflows, which grain size you're looking at is going to tell you a lot about the temperature of the gas that you're observing, which is one of the things that we want to constrain in the studies of the baryon cycle. So I'll go ahead and just put up my finishing slide, and thanks.
Thank you, Helena. We have time for a couple of questions. Yes, there.
So thank you for the talk, very interesting. I would like to ask, so we know that the cosmic dust does actually not peak at redshift 0, instead they peak around redshift 2. Mm-hmm. And when you have a higher dust amount at higher redshift, what will this effect will turn to be? Because, for example, with higher gas density and higher temperature, do you expect the dust to survive further? Or?
Yeah, that's a great question. So these simulations that I ran, the galaxy simulations I ran one that was more for a local or low redshift nuclear starburst galaxy, and one that was more analogous to a higher redshift galaxy. And the higher redshift galaxies, because they have just a higher star formation rate, they eject way more cool gas out of the disk. And I didn't get a time to make this point, but having more cool gas in your outflow creates a lot more opportunities for dust to be shielded from destruction in the hot gas. So in the galaxy simulations, we measured boosted dust survival rates across all of the grain sizes simply because of this environmental shielding effect. So yeah, at higher redshift, I would say that it's probably even more efficient at getting dust out of galaxies.
Fantastic, thank you.
Time for a final question, if any. Yes, Vadim.
Really awesome. So, in terms of the amount of coal gas, some of it can come from the cooling of the hot halo on the wake of this destructive cloud. So I was wondering if it's possible to make any constraints about how much coal gas comes from the ISM versus being just by observing both the ice and the dust.
Absolutely. So the direction that this work is going in is I have these large data sets, high resolution data sets that are resolved to similar spatial scales as these observations of like the M82 galaxy, for example. And these are probing specifically polycyclic aromatic hydrocarbons, these really tiny dust grains that are destroyed in like basically instantaneously. And you know, my work has shown that, yeah, hot gas condensing onto cool gas and outflows, you wouldn't expect to see any dust, any of these small grains in that gas. So yeah, I think by comparing these data sets with these observations of these tiny grains that are really strong probes of cool gas is, yeah, a way to tell, you know, how the cool gas is forming.
All right, thank you, Helena, for our report. And next to our final speaker, Jacob Nibauer from Princeton.
Okay, thanks so much for the opportunity to speak. There's a theme here. I'm also a final year grad student, and I'm going to be talking about some recent work on mapping the kinematics of stellar streams to constraints on substructure in the galaxy. So the focus is on kinematically cold, typically, globular cluster streams, which dissolve in a massive host like the Milky Way. And what's so useful about these is that their structure is quite predictable in a smooth galaxy model. It's regular, uniform, and quite smooth due to their low velocity dispersions. However, the catch is, at sufficient depth, every stream we've observed in the Milky Way so far appears to deviate from these smooth expectations. And there's one example that maybe you've seen a lot, and perhaps too many times, but here's the most well-known one. It's GD1. It has a spur, a gap, and some density wiggles. But now there's more, where we see asymmetric tidal tails. We see other evidences of spur features and density wiggles. And of course, the underlying question here that I'm thinking about is, what is driving these density features? And more so, can we use this to learn something about dark matter substructure? So we've heard this earlier, but in cold dark matter, you have a plethora of low mass subhalos all the way down to Earth mass subhalos. And we'd like to know if that's true, right? These would lack a stellar component. Or if the dark matter is warm, there's a lack of low mass subhalos, or you can get self-interactions. But the idea is, how do these different density fields affect stellar streams? One simple example here, just looking in on-sky coordinates in a simulation. I'm going to perturb this stream with a 10 to the 7 solar mass subhalo, wind the clock forward, not much has happened, 50 megayears later. Look half a gigayear down the line, and you get a gap. And that's been sort of the consistent story in the literature for a while now. But there's another dimension that we can look at, which is radial velocities. So here it's a similar story along the x-axis. That's the same as before. But the y-axis, you basically get an impulsive kick to the stream, and it leads some of to the left and to the right of the impulse. You get an increase in the velocity and a decrease in the velocity. And that can be completely understood in terms of the impulse approximation. There's a lot of intuition to build there. However, this is a very simple picture. CDM, you expect many subhalos, many impacts. What does it look like in that scenario? So that's what I'm showing here. In blue, there's no subhalos for a PAL5 type stream. And in red, you have a population of CDM subhalos. You see that there's these density gaps and bifurcations. The kinematic picture is just, quite frankly, very messy. So blue, there's still structure, no subhalos. You know, the stream isn't completely flat, but you can predict what it looks like. But it gets quite chopped up when you add in all these low mass perturbers. And maybe the simplest thing you can start to do with this is just to histogram the velocities and see, OK, if we were to make observations, do the observations look like the blue histogram or the red one? Huge caveat, though. This is a very stochastic process by nature, right? There's draws from the subhalo mass function, and there's also draws from an orbit distribution function. So even for a fixed CDM mass function, you can get many versions of the same stream. So what we can do is just draw more realizations and see how these different CDM realizations shift things around. And there's quite a large range of models that you can get out of this. And then just do that like literally a million more times and build up distributions that look like this, where in red you're seeing the culmination of something like 6 million different simulations, so perturbative calculations, and in blue, no subhalos. And the result is very intuitive. If you have all of these low mass, noisy perturbers in the acceleration field, it raises the stream's temperature, you get kinematically hotter. So what you can do then is to start to do statistics on this, just take standard deviations and ask, if I change the abundance of subhalos, so really the normalization of the subhalo mass function, how much injected heating do I get on the stream? So that's what this is showing. CDM range of outcomes is in gray. If you have 4 times more subhalos, you make the stream hotter. 70% less subhalos, you make it colder. So it's quite simple, but it's good news, because it says, OK, if you can measure stellar stream velocity dispersions, then you have a mapping to something about the number of low mass subhalos, down to 10 to the 5 here in this case. So that motivates looking at data sets like this. I'm sorry, it's still going to be GD1 today, but hopefully I'll end on prospects for doing this with many more streams. But what's great about GD1 is it's been observed a lot now kinematically. So we take 4 different spectroscopic catalogs. We do some hierarchical modeling to account for these very heteroscedastic errors and try to constrain binarity using repeat observations, ultimately to get to the intrinsic dispersion of the stream, which is what I'm showing here. So this is the measurement of the intrinsic dispersion and uncertainties as a function of 3 different bins along the stream. And what we get are numbers that are around 5 kilometers per second in the middle, 3 on the right, and something that's consistent with like 1.1 on the left, roughly. So the simplest question you can ask is, where do the unperturbed models without any subhalos fall in this space? And the answer is it depends weakly on the progenitor mass. So these are a pretty broad range of progenitor masses. But unperturbed models are at like the 0.7 kilometer, 0.8 kilometer per second level. So what that means is, with these simple models, there's like a 4 kilometer per second deviation. And we would like to know, OK, if we want to explain that discrepancy with dark matter subhalos, not to say that it is, but if we entertain that, what sort of subhalo population would do it? What do we need? Does it look like CDM or something else? So that's what we're going to do here in a moment. The 2 sort of knobs we're going to turn is how many subhalos there are. That changes the outcome of the streams. The other one that is sort of underexplored here, in the context of streams at least, is the mass-size relation. So at a fixed subhalo mass, what if we make subhalos more compact, more dense? That has a pretty powerful effect as well. More dense perturbers are going to do more damage to the stream. Jumping straight to the results on the subhalo mass function. So this is from those 3 data points. I'm going to start to build up this plot. CDM, again, you have subhalos all the way down. If the dark matter is warm, you get a suppression at the low mass end, depending on the particle mass. At the high mass end, we can start to put points there from just counting the classical Milky Way satellites, just counting their number. And finally, some bounds from GD1 kinematics. And what you can see, 68% level, there's nothing really unusual here, right? The subhalo number density in our models is perfectly consistent with CDM expectations. That's enough to explain the 4 kilometer per second discrepancy. Caveat, though, these are marginalized over the mass-size relation. So there's possibility that some of these subhalos are much more compact than CDM. And that's what I want to show here for a moment. So here's the constraint on the scale radius of subhalos relative to CDM. So 1 would be CDM expectations as a function of the fraction of mass in subhalos. So for context, the CDM expectation is like 5 to 8%. At the 5 to 8% level, we do at the 95% level find a preference for more compact subhalos. But it depends on how you slice this. So specifically at low subhalo mass fractions, you have less impacts. You require your subhalos to be like 60% the scale radius of CDM and below. So you need them to be quite compact. At higher F sub, you have more impacts, and the mass-size relation is more consistent with CDM. So the bottom line with this plot, I think, is that we can explain the data with either one very compact but massive perturber, so at the 10 to the 8 and above level, or the expected like 100 number of subhalos that are slightly more compact than CDM. So that's the idea. The final thing I want to show is what if we allow for a mass dependence in this relation. So this assumes that this factor here, RS over RS CDM, is the same for all masses. So simple modeling, what we can do, throw a broken power law at it, and ultimately derive constraints on a mass concentration relation. So that's the final thing that we get out of this, where again, you see these bounds. Our prior is set by the black line up there. You can ask me about that at the end if you'd like. And it's exciting because we can start to compare this to strong lensing. So of course, other galaxies, these are constraints from 11 strong gravitational lenses. Maybe even more interesting, look at predictions from numerical simulations, where with field halos, we're maybe 2 sigma deviant from the mass concentration relation of those. However, for subhalos, tidal effects can make the central densities higher, which leads to larger concentrations. And there we're at like 1.7 sigma deviant. So not really a tension, but maybe a hint of something happening at the low mass end. So that's the summary there. At the high mass end, there's no preference for anything that's more or less compact than CDM expectations. But at the low mass end, at roughly the 2 sigma level, we need subhalos to be a little more compact to match the data. So I hinted at this at the beginning, how we've studied GD1 extensively, and this is a new phase space dimension to tackle the problem at. But I think it's exciting from a single stream, we can get at constraints on the abundance of subhalos and even in their internal structure. To date, there's well over 100 Milky Way streams. So I think the exciting thing that is being developed largely here at CFA is the VIA project, where spectroscopy from VIA with precision radial velocities will be able to improve these types of constraints by well over an order of magnitude just by combining streams. And of course, the velocity precision helps as well. So that's exciting for precision. The final thing I think is, to me, what's most interesting is, are all these streams telling us the same story? They're chasing the same galaxy. If we're really measuring low mass substructure, then we should be finding consistent results sort of as a function of radius. I will end there. Thank you.
Well, you timed it to the second. Yeah, we have time for questions. Yeah.
So I'm curious, when you were showing us the realizations of individual streams, it's not always that they're more dispersed, right? Like they can be shifted, that sort of thing. So how does this kind of play out in a world where you only get to see one stream at a time, rather than we're not actually sampling a million?
Totally. So yes, and as it turns out, is it up here? No, it's this one. The answer, why don't I just give you the words instead of looking for the plot? Yeah. The answer is just, you're right, completely agree. That's why you need to go to many streams. You're going to get more robust constraints there and physically tighter error bars. But also, it turns out that there's a lot of variance with CDM, right? The distributions are broad, but GD1 sits even beyond CDM. So at the 95% level, it's still at the tail end of that distribution. So that's a sort of robust statement for kinematics. Okay. Beyond that, not as robust, and that's why the constraints are actually bounds and not closed contours. But more streams will help a lot with that.
And do you get to, does like a spatial chunk of a stream count as a realization? Like you binned it across 3 stripes in space?
So we use all 3 bins. I was really focusing on the middle one where the dispersion was highest. Yeah. That dominates the constraints, but it is the full phase length, is used.
Interesting.
Yeah.
So you might have seen this recent Nature paper, claiming a 10 to the 6 solar mass, halo detection, VLBI, strong lensing. Where does that fall in the concentration halo mass?
I've just been traveling around too much. I haven't calculated it yet, but I think it's quite high, and I don't want to give you a number, but yeah, I don't actually know where it falls exactly. But I wouldn't be surprised if it's going to be above 80, perhaps, just roughly guessing.
More questions for Jacob? Buddy.
So is this concentration of this Nibauer NFW profile?
Right. Well, these are actually Hernquist subhalos, but we use C-2, so it's the concentration where the slope of density profile is -2. So yeah.
I see. Okay. Yeah, I was wondering what's the correct profile to use at this low masses?
Yeah.
Is there
I would love to know the answers to that question. I think one thing we could try next is what if we switch out profiles and see how these constraints shift around. My guess, I've done some preliminary testing, it doesn't change the story very much. Yeah.
So I actually have a question for you. What's the constraint that you get on the work dark matter particle mass, and how does that compare with Lyman alpha forest or stuff like that?
Yeah, so it's something like the half node mass is like 8.5, 10 to the 8.5 solar masses, which is actually a pretty high upper bound. But it's a little deceiving because we can have that strong suppression in the mass function, but we need the subhalos to be quite compact, which is not what you would find in warm dark matter. So I don't know the numbers for Lion alpha, but I do know is from these results we actually disfavor warm dark matter and favor the scenario of more compact subhalos, but at the CDM number density.
Okay, one final very quick question. If not, let's thank
Thanks.
Jacob again. Let's thank all our speakers. Yep.
Good. Have a fine day.